So in section 3 we found the exact value of certain angles such as 30, 45, and 60 using some special triangles. So what we're going to do in section 4 is we're going to actually try to find the trigonometric values of lots of angles, what we call general angles, and then introduce what's called the unit circle. So if I want to find the trig values, say the sine of 200 degrees, let's say. Well, the problem with that is, well, we really don't know a triangle, a right triangle for sure, that has an angle of 200 degrees. So we really can't use a right triangle idea per se to find these angles. So what we do is we use what's called the general way to find the trig value of any angle is to use standard position. So if I have an angle, a standard position, that means we have an angle that has one side on the positive x-axis and then one side on this kind of terminal ray. This one we did in quadrant 1. Now if you think about this angle and this ray, if I pick any point on this ray, it is some point xy. Now I could pick this xy there, I could pick this xy here, it doesn't particularly matter. But if I think about this xy, then what I really get if I drop a perpendicular line down to the axis is I get a right triangle. So in this right triangle, since it's in the coordinate plane, we go over x units, so this is x, and we go up y units, so this is y. The hypotenuse of the triangle we call r, but by Pythagorean theorem, we know r squared equals x squared plus y squared, and then of course if you take the square root you get this relation right here. This is r equals the square root of x squared plus y squared. Now the good news is, since we now have this triangle based on this, it doesn't really matter if I had an angle that was over here, it would still have a point xy on this ray, and I could still go down and make a triangle. Just the only difference in quadrant 2 is the x could be negative. See, because you go this way, so x would be negative. So really, if you think about this right triangle with x, y, and then r, it could really be applied to any angle in the standard position. So if we look at this triangle, and we have this little angle theta here, which means this is the hypotenuse, this is the opposite, and this is the adjacent, then based on this triangle, we can actually set up some trig ratios. For example, we can say sine of an angle in standard position with a point xy on the terminal ray, and that's the key thing, it has to have a point on that terminal ray. Then we know the sine is the opposite over hypotenuse, it's y over r. And you can see the other ones are pretty much the same thing. Cosine is x over r because that's adjacent over hypotenuse. Tangent is y over x because that's opposite over adjacent. And then I just flip sine, cosine, and tangent to get cosecant, secant, and cotangent. So we actually define the trig value of different angles based on any point on the terminal ray. And that's a key thing. You have the angle, here's one ray, let's say the other one's down here, it's any point on this ray. So if you have an angle here, you just have to find a point on this terminal ray. Which if you have it, that's great, but sometimes that can actually be very tricky. So let's look at an example of this. We want to find the 6 trigonometric ratios of theta in standard position whose terminal side passes through the point negative 4, 5. Now I don't particularly know what this angle is, but it says if I have a point on its terminal ray of negative 4, 5, so that's this point here. So we go this direction for this initial ray, and here's my terminal ray that has to go through that point. So the angle theta could be here. It also could go the other direction, but we'll just say it goes here. Because any angle that basically ends on this ray is going to have that idea. So if we remember our relations from the previous table where we had the y over r and all those things, well, since this point is negative 4, 5. We know the x is negative 4. We know the y is 5. And r, by that little equation on the previous page, is the square root of x squared plus y squared. So that would simply be the square root of negative 4 squared plus 5 squared, which is the square root of 16 plus 25, which is the square root of 41. So now we have x, y, and r. So the sine of any angle theta is y over r. So in this case, that would be 5 over the square root of 41. I also could make the triangle if I want by making our perpendicular line. This side would be negative 4, this would be 5, this would be square root of 41. Always using the angle here by the origin, opposite over hypotenuse would also be 5 over root 41. Cosine of theta is r, or x over r. So that's negative 4 over the square root of 41. Again, for this mystery angle, we really don't know what the angle is, but we can find the trig ratios of it. Tan is x, or y over x. So y over x in this case would be 5 over negative 4. The other three ratios are very easy. I'll just flip the sign to get cosecant, so that's square root of 41 over 5. The secant of theta is the square root of 41 over negative 4. And the cotangent of theta is going to be equal to negative 4 over 5. So again, if you know this point, and basically everything I did on this page was predicated on knowing that point, knowing one of the points on the terminal side of the angle. Really the rest is just really filling in numbers for the appropriate ratio. Okay, so now we can kind of find all the different trig ratios of basically any angle. But the key thing is, if you know the point on the ray, find that point on that ray can become very difficult. So one way that we do it a lot of times, a kind of easy way to do a lot of special angles, is with what's called the unit circle. Now the unit circle is simply just a circle where every point on this circle is basically 1 unit away from the center, which we put the origin. So if I take any point on the circle, let's say I take this point here, and I measure this distance, it is 1 unit. You can all obviously see from here, from 0, 0 to 1, 0, that's 1 unit. From 0, 0 straight down to 0, negative 1 would be 1 unit. Everywhere on this circle is 1 unit away. So really, the distance from here to the point is always 1. So if we think of our triangle like we had before, we still have an x, we still have a y, but the r essentially is always 1. So r, in our case, in those previous ratios, for a unit circle is always 1. And since it's always 1, if we know this point on a circle, which is actually a little easier to find, then we can find our trig ratios. So what you see here below is essentially an even easier relation if you make r equal to 1. And the first two are really, really important. The sine of the angle is simply just the y-coordinate. It's the y-coordinate on this circle. So if you know a point on this circle, the sine is just simply the y. The cosine is simply the x-coordinate. So by knowing the x and y coordinate, right away you know sine and cosine. The tangent is y over x, the y coordinate divided by the x, same thing as before. And the rest are just flips, so I'm not really going to spend too much time on those. So really quite amazing if you know a point on this circle. So let's say we have this unit circle. If we know this point, x, y, well, since we know sine is y and cosine is x, so if we have this angle, this could also be thought of as cosine theta, comma sine theta. So really you know the cosine is sine right away by knowing that point. Basically the same thing we did before, but the r is 1, so it just becomes a little more simplified. So again, we have to know the points on the unit circle to do some of this stuff, and we will actually have a nice handout here on the next page to show you a lot of these points. But let's just say that we know some of these points on the unit circle. So let's say this point, square root of 2 over 2, square root of 2 over 2, is on the terminal ray of some angle theta. Find the 6 trig ratios of theta. Well, the only ones you really have to remember are these. Sine theta equals y, cosine theta equals x, tangent of theta equals y over x. So in this problem, since we have the x and y here, remember this of course is the x, and this is the y. So we know the sine of the angle is simply the y, so the sine is square root of 2 over 2. We know the cosine is x, so the cosine of this mystery angle is square root of 2 over 2. Now the tangent is the one that gets a little tricky. So the tangent of the angle would be x over y, or y over x, so that's square root of 2 over 2 divided by the square root of 2 over 2. But we should know, since this is basically the same number, you can cancel these 2's, you can cancel these square root of 2's, so this is just simply 1. The other 3 are just the flips of the first 3 we found. So the flip of square root of 2 over 2 would be 2 over the square root of 2. And we could, of course, rationalize any of these. Same for secant. Cotangent, we're just flipping 1, so we get 1. You could rationalize any of these like we did in the previous sections. Like for this one, I can multiply this by square root of 2 over square root of 2. This would give me 2 square root of 2 over square root of 4, which is 2. So this would cancel and give me the square root of 2. So 2 divided by the square root of 2 is the same as the square root of 2, just a different way to write it. So here's another problem where we have another point. So we have this mystery point on the terminal ray of theta, wherever that angle would be. So again, the sine of the angle is simply the y, so that's negative half. The cosine of the angle is simply the x, so that's negative square root of 3 over 2. And the tangent of the angle is y over x. So in this case, that would be negative half over negative square root of 3 over 2. Now a really easy way to simplify this, well the 2's cancel, the negatives will cancel, become positive, so this is just 1 divided by the square root of 3, because you can see those bottoms will cancel out. And that's pretty much going to be true for most points on the unit circle. I can then find my other 3 just by flipping. So if I flip negative half, I get negative 2. If I flip cosine to get secant, I get negative 2 over the square root of 3, which if I rationalize, I know that's negative 2 square root of 3 over 3. And the cotangent, if I flip tangent, is just going to be the square root of 3 over 1. So it's just square root of 3. So what we have now is we have basically the unit circle. So what you'll see is a lot of these special angles, such as 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360, and 0, we basically have the points on the unit circle. So what we just did, we basically have these points. We know that this is the point on the unit circle for the angle of 30. You'll notice it also has its radian measure of pi over 6. So depending whether you're doing radian measure or you're doing degree measure, it has both of those on there. So really this is basically the point. So all these points, the x is the cosine, the y is the sine, and you could do the tangent and find all of them from this circle. So really it's just a neat way to find all these different points. In future coursework you may have to memorize this circle. That's not an unrealistic expectation, but for our course your course will be able to use it. So if I want to basically find some values of these special angles, really all I need to know is the points that correspond with these different angles. So the first one says I'm looking for the sine of 120. So if I go to my unit circle and I look, what's the point at 120? This is the point I see at 120. It's -½ comma square root of 3 over 2. So we just have to figure out which one of these do we need. So this point comes from the unit circle. So the sine, we know, of any angle, or the angle, is always the y-coordinate. So the sine of 120 would be the square root of 3 over 2. So again, using that unit circle, I just look what the point is, and I know sine is y, cosine is x, tangent is y over x, and then I can find the rest by flipping. So if I go to 300, because I want to find the cosine of 300, the point at 300 is 1/2 comma negative square root of 3 over 2. So since I want the cosine is the x value. So the cosine of 300 will be the x value, which is 1/2. Okay, let's look at the tangent of 225. So again, I'm going to go to my unit circle. I'm going to go to 225, and I see the point is negative square root of 2 over 2, negative square root of 2 over 2. Now tangent is not x or y, tangent is y over x. So the tangent of 225 is going to be y divided by x. So that's negative square root of 2 over 2. Divided by negative square root of 2 over 2. But you'll see the 2's will cancel, the negatives will cancel, and the square root of 2's will cancel. So everything cancels, so it's just 1. So the tangent of 225 is 1. Now here's an interesting one, cosecant of negative 150. Now negative 150 is not on our chart. So to get something that's on our chart, we can do a really simple process. All we have to do is basically add a full rotation. So if I add 360, I get 210. So since the circle is a big, it goes around and repeats itself, the cosecant of negative 150 is the same as the cosecant of 210. So all I'm really going to be using is I'm going to be using the point for 210 because that is on our unit circle. So you can always add or subtract, and that would work really nice. So the point for 210 is negative square root of 3 over 2 and 1/2. Now cosecant is not one we find directly on here, but we know cosecant is the flip of sine. And there's my sine value. So basically I'm going to flip 1/2. So the cosecant of negative 150, or 210 for that matter, is going to be just positive 2. Because I flip positive half and I get positive 2. Okay, let's look for this one for the secant of 4 pi over 3. 4 pi over 3 is on my chart. It's also at 240 degrees. So 240 or negative or positive 4 pi over 3 is negative half negative square root of 3 over 2. Now if you recall, secant is the flip of cosine. And the cosine is always going to be this value here. So basically we're going to flip the negative 1/2. So the secant of 4 pi over 3, which is in radians, also 240, is going to equal to negative 2. Now the last one we have is the cotangent of negative 3 pi over 4. Now 3 pi over 4 in in degrees is 135, so this is really the cotangent of negative 135. But that's not really on our table either, so we'll use the trick we used above. We'll take negative 135 and we'll add 360. So if we take negative 135 and add 360, we'll get 225. So the cotangent of negative 135 is the same as the cotangent of 225. Now we already had the point for 225 above, but we'll write it again. It's negative square root of 2 over 2, comma negative square root of 2 over 2. So cotangent is the x over y. It's the reverse of sine. Tangent, pardon me. Tangent is y over x, so cotangent is x over y. In this case, it doesn't matter because they're the same number. So negative square root of 2 over 2, negative square root of 2 over 2, just like above, everything will cancel. You get positive 1. So a couple of techniques for finding the exact value of lots of different angles, but it really all comes to finding that point on the terminal ray, either by giving it, finding it, or using the unit circle.